Swayam Prabha. Digital India. Educated India.
All right. Now we will continue to calculate those Q we would like to calculate. So in this case, so we will have ny equals 0, sorry, ys equal to 5,000. And we know Q, the gradient of the longshore transport will be QYN, then divided by YS, YN. That's a gradient change. So now problem is what is a QY we are having, which is 0.77. That's a K. So just now we had some discussions on the K from I think it's a Louis. Yeah. So from her study, she used a different K value, depends on the sediment, the D50 values. And from her research, you can see the variations in the seasons change. From January to December, all the values is different. Varies from 0.49 up to 0.9 something. So the variation range is very large. So in that case, I would suggest that you use the varying value. Do not use that average. But every time step, you use those, the most close to the values to your calculations. So now we're looking at this formula we are having over here. It's a GHB 52 and sine 2 theta b. And why I have a negative values over here, the negative sign. So the negative sign I write here, why I have a negative, okay? So the negative sign is to account for the transport, in this case, in negative direction, because the wave from east to southeast, right? So the wind direction, the dominant wind direction or wave direction will be from here. But our positive direction y is going down. Yeah, that's why we need to have a negative sign. So remember that. That's really important. Otherwise, the result won't be correct. So wave is from south to north. But positive y is north to south. So that's why I have that. So now I will be able to calculate -1 and then (1.4 to the power 5/2), then sine 2 times 10 degree. That's in the south direction. And also we know this is a -8.101, 10 to the -2 meter square per second, cube per second. So that's for the south. Then at the north point, then we have the QY north. The only different over here is the wave condition is different. So all this calculation is the same. Then we have wave height is different, the breaker height, and also we have the angle is different. So that, sorry?
North direction is positive.
Still the same.
Same.
Still the same because the wind is going upward. Yeah, but the direction is going down. Yeah. So what we are having over here is 10 to the -1 cubic meter per second. So so we will have our QY, the gradient over the y direction will be approximate to this one divided by ys minus yn. So which will be -8101, 10 minus 2, then minus 1.052. And 5,000 minus 0, which equals to 4.833 10 to the -6 cubic meter per second per meter, and which equals to 152.4 cubic meter per year per meter. That's where we convert to the year, because our another condition is per year. So now is for us to calculate the QX. QX will be equals to, if we have that formula, back to that formula, what we are having over here. So what we are having over here, QX will be equals to so we will have 152.4 minus 1 minus 0.3, the porosity, times closure height plus the berm height, times 1.6, which is given. So we will have so for this one, we will have this QX actually is 142.3 cubic meter per year per meter. But if you want to see the total area of that, then we need to times 5,000, because that will be the total stretch of this. Here is like a per unit length. And because now the QX is positive value, which means the cross-shore sediment is towards the coastal line. So that's for this example.
The sediment transport, the negative sign using because the sediment is moving from north to south.
Yes, we use a direction. We assumed the positive is from north to south.
Actually, the wind is blowing from east to southeast. So it will come the transport towards north.
Yeah, so if you do that, you just change the coordinate direction, then it's just a sign difference. Then, is that what you mean? So for example, over here, if I change this y positive, if I change that, and then over here, you don't have the negative sign. The green sign, then you don't have that. But then they are agreed to each other. Your wave direction and the coordinate is the same. Then this green sign is a positive.
Y is positive north, wind direction is north to south. You mentioned it there.
Yeah, because our wind direction is east southeast, right?
Yes, ma'am.
So which means the sediments basically should be going upwards.
Upwards.
Yeah. But just because my coordinates I defined here, I use the positive downwards.
Positive is downwards.
Yeah, that's just the coordinates, right? So I can also change here y going up, but then here I just remove that green negative sign. The result should be the same. That's just like a coordinate. Like sometimes the y coordinate going down is a positive, right? Sometimes you have going up, like against the gravity is a positive. Then your g just you put a negative value. Is that your question? Yeah. So you can try. You change the coordinate to another direction, remove that negative sign. Are you getting the same answer or not? You should. But that's very good, like how you solve the problems. Once all those coordinates and all those signs is clear, then which means you have a good, very good understanding about the problem. Yeah, thank you. Okay, then here actually is the same example, but I still ask you over here. So beach nourishment is the addition of the sand to a coastal system. We are still using the last example, but now we assume that all parameters stay the same. What is the annual rate of the nourishment that would be required in order to stop the shoreline retreating? So all the calculation, all the condition is the same. We know there is a 1.6 meter retreat, right? Now we want to stop that retreat. What we need, the nourishment we need to stop that. You just using the same formula. Everything is the same. The only difference will be here. This part. This one goes to 0, correct? Because we don't want to have any retreat. But we have nourishment, which is a source. So this one is what you need to calculate. Other things is all same. Yeah, so that's another way. So you can see this is this much of the sand for that 5,000 meter stretch of the coast. You need this much of sand. Now we come to the numerical part. I want to, are you familiar with the finite difference method? Yeah, okay, good. So that's just a quick overview of that. There are many different numerical schemes. Here we are using the finite difference method to do it. the fundamental of this finite difference is based on the approximation. You are able to define those 2 points, the next 2 points. So if you want to find the values of this point, you are able to use neighboring point to do the calculation. So if you want to calculate this one, you are able to use a neighboring point, either one of that or both of that. Okay. So that's we use a Taylor series to do estimation. One is a upwards point, and one is a backwards point. So when we are looking at that, first is for the forward difference approximation. For the value at this point, you use a forward point. So that's what we are having over here. So for our case, for example, we have this one. So you are able to get this approximation by using xi minus xi minus 1 and divided by delta t. So that's we are going to use. So basically it's either backwards or forwards. And also there is a central that's using 2 points. So here then you are seeing this is a second order. So when to use which one, that all depends on what's the boundary condition you have. Yeah. So, and also the different transport mode. So you are using as well. Now we look at the example over here. Question is the same as our last example, but a little bit different is consider a 5.3 kilometer stretch of a coast in the northeast direction. So that's the same. Ocean to the east. The predominant wave direction is again from east-south to east. At the southern end, typical breaker is given, and the angle is given. Angle is also given. And also the northern end as well, the location and also the angle. And the breaker index is also given. Now we look at the beach profile along the section are similar with the slope. Near the breaker point is this. The sand is a coarse. And also with grain size is this. And also the depth of closure is 16.2. The berm height is 3. That's a given condition. Very similar to last example. Yeah, nothing special. Now we have the average shore normal sediment rate. So last example asks you to calculate QX, but here QX is given. So we have the data set from 1999 to 2021. So we have yearly data. So it's not constant, it's changing with the time. So the file is also given. So that's, later you will see the file. And there are no sinks or source. So we have no dredging, we have no nourishment for the sediment in the control domain. The erosion rate can be calculated using this one. So that's XS you are able to calculate by using this formula here. And those given conditions are all listed here. There's no problem, similar to the equations. The aerial photo of the stretch of the coast in this period indicates shoreline location in some years. So you also have some like a location from the photo we have taken. So you know what is the XS, another file you will see later. ask you use a Python code to develop a numerical model and present the location of the shoreline from 1999 to 2021. And also we assume at 1999 the location, the reference is 0. So using that as a reference point. Again, also you need to evaluate the accuracy of the model. So are you able to imagine what's that? What's this problem are asking? So I also give you, this is 2 data file. So you are able to see that's for the shore normal transport. That's for every year. The data set is here. It's given. First column is a number of the year, and the second column is data. And the unit is here, cubic meter per year per meter. And the second line, the second file, which gives you, they have the measurement from the aerial photo. For 2001, you can see it's 2.2 meters. And then for 2006 and 2000, so that's 2021. So you are able to see the variation, the change of the beach profile. So that's a data set. But from last calculation, you remember, that's QX. You need to include that for your calculation. But do you need to have this one in your calculation? So you are, based on this one, you are able to do that 1 year by 1 year, right?
1 year by 1 year.
You can do that manually, 1 year by 1 year. Just take a bit of time for you repeat to calculate, okay? After 1 year, what is the excess? Then you calculate another year, what is excess? Of course, that's just time consuming, but it's doable. So here, because we are able to use a program to do it for us, so that's why we write a model. So if you have 100 years data, then you can do for the following 100 years, then, or previous 100 years, what are they? So for this data column, just used to compare with your model result. Yeah, like if you are using some other flooding model or wave model, you always have the measured buoy data, for example, to calibrate your model or to validate your model. And also here, again, you may, so like this K constant, that can be a calibrate factors. If they don't agree, should we adjust that K value to get the best fit? Yeah, that can be that. So that's for this one. Basically, what you are going to get is, so I just draw roughly, if this is XS, initially XS is here, 0, right? Oh, sorry, this is a year. And this is XS. So you can see this is 2000, this is 1999, and this is 2001 and 2006. Yeah, and so on. You have this 2011, 2016. You can draw a little bit longer, and 2021. So you have this is roughly here, and this one is roughly here, and it's keep increasing basically. So that's a measurement. So you are doing the modeling. So you will have a data set, like for the all years. If all those dot point is on the lines, then you got the perfect models. But you know we won't be able to get that. So that's what you are going to get. Your model, the line, that's what you, for every year, what is the value of XS? That's what you need to calculate. Yes, XS location, yes. That's right. Because you have the reference is 0, so you know the changing, then you will know the exact location, right? And then next one, you also calculate the changing, of course, based on the reference point, you will know where is the next one. So that's basically this model will do. So the reference point is origin of the coastal line. Shoreline position in meters. So, okay. So which means initially, for example, initially that's our beach, right?
Towards offshore or towards onshore? Towards shore, offshore or towards the shore? Land side.
Positive.
X is positive.
Yeah.
Land side.
Yes. Towards
the
towards the shoreline. Yeah. So, for example, initial here is 0, but then 2.2 you may be here.
The position.
Yeah. And then 5.
Erosion.
So that's again, that's our, because that's our x direction we defined over there.
That's why we define X direction.
Yeah. Okay. Yeah. Good. Yeah, we have to make that clear. Then you will also be able to explain your result clearly. That's a numerical part. That's the equation we are having. We are going to use, right? And we don't have this one. That's 0. Yeah, that's 0. So we use a finite difference to write it. Yeah. So this will be the key part. So that will be the key part. So when we are having this one, we will have because we are using this initial point, later I say initial point. Okay, then we rearrange everything. This is a 0, this is a 0. So everything will be rearranged. So we don't need to have that one. So the whole thing will be, this will be the one you calculated. And this will be based on the last year's position. So our initial condition, T1, that's for the year 1999, that's a 0, our starting point. And also that's for the first year, the location is a 0. Because in Python, the index starts from 1. In MATLAB, start from 0. Here, because we are using Python, so we use the T1 and the X1, that's equal to 0. That's a reference point. So what you are able to calculate. So the first calculation will be X2, which will be equal X1 plus, correct? So based on the initial condition, that you will be able to calculate XS2. That's no problem. So you will be able to find out year 2000, where is the XS? That's no problem, yeah. So after this calculated, definitely you know what is the XS2. So in the next iteration, because it's a model, then you will calculate XS3. Then this time it's based on SX2. All the others,
Same.
not exactly same. You will get from the file. There is a file. Yes, yeah, but the variable is, but depends on which year. It will extract the data from that file, different year. So not constant, but it's from the file. It's a given condition.
QY is not given.
Q,
Y is.
yeah, you have to calculate. You have to calculate, but it's a constant here. It's a constant here. Because the wave condition, we didn't give you the changing wave condition. So this will be the limitation of this model, not the model, the data set. If you have the every year's wave condition, then you can, same like a QX, you have the every year's QX. If you have every year's wave height, you can also read another file. Then you have a more accurate result. So that's all depends on what information you have. So you are able to calculate. So here, if we say this one, it will be QX. Here is a QX1. And then you have this QYS minus QYN, because here is a constant. But of course, you have to calculate this before you are using it. This is a constant, and this is a constant. And here is a delta T. In the next iteration over here, that will be QX2. Yeah, because that's the next year's data. And so on, you do the same thing. But here is the same. Or the other is the same. And then you do the next one, you do next one, until you did the last one. Okay, so the files I sent has both the MATLAB file and the Python file. Have you all got the file?
No, wait 5 minutes.
Oh, okay. No problem.
You are sending by mail? Sending mail. She is sending the same.
And everyone has internet, right?
Mail address. The mail address. Mail address. Download the.
Have you got your file?
అందుకే పెన్ డ్రైవ్ ఇది ఫైల్ డౌన్ ఉంటుంది.
You got your file.
I got file, it's not downloaded. Pen drive it is. It's loading. Not detected.
So now we can go through.
1 minute.
1 minute, okay.
Everyone got the code? And internet is there, right?
Okay. All right. So either way, there is one is a MATLAB file and another one is a Python file. So the Python file, the name is a question 2. Just open it. And also there are 2 data files as well. So if you are familiar with Python, you know the first 2 lines are just the import the library. One is a NumPy. In engineering, we use NumPy a lot. Yeah, because of the data analysis, we use the NumPy. So that's just a library. And the second one is for the plot. So basically, that plotting is very similar to MATLAB plotting. So that's another library. So for this line, that's for the plotting. Okay, so that's a Python. We need to have those library imported. And then the next 2 lines, this just give you a high resolution of the figure you are going to generate. So it's still like if you don't have that, you will have the resolution of the figure is not as good as this. So this you set up the DPI, so you can have even higher. So then coming to here, this will be similar, like you are solving any engineering problem. We always define the given condition at the beginning section. So that's all those parameters which has been given. So later you don't need to use a number, you just use a variable name. So that's for all of those. Then you could be looking further down. This is the first file. The first file is a sediment. It's a sediment. So for every year, what is a shore normal sediment, right? Yeah. So you can look at the data set. The sediment data set is here. If I click it, you are able to see it, right? So that's a data set from 1999 to 2021. All right, now I go back to my code. And I put the first column, that's the year. And then the second column, that's the sediment rate. That's the QX. Okay, so that's just a load the file, put those files in the variables. Yeah. And normally before that, I would plot out the data set to have a look. So here is just to use that imported library, I do the plotting. So like here, if I run this cell, you see I have a separate cell. So this is a top cell. I have the hash and double percentage. So I separate the cells. So I just run the first cell. Then you are able to see the result. That's the figure. So that's a figure, right? So that's a year, that's a QX. First, I just try to inspect the data set you load it in, the visually to inspect it. So every year, how much the sediment transported in the short normal direction. So that just shows the data set. Okay, that's for plotting. Up to here is a plotting. Now I calculate QYS and QYN. That's like we do the manual calculation. Here we use a code to do it for us. Any problem? No problem. Mm-hmm. Then you do the. Any question? No problem, right? Mm-hmm. Okay. Then you calculate DQY, and then I convert to the year. Okay. Mm-hmm. So I have a comments at the end of each line, so it should be easy to follow. Uh-huh. So that's everything you're able to see.
We can change the values in the variable exposure. We can change the values.
Which value?
D50, gamma, HBS.
Yeah, that's you change at the beginning.
Yeah.
Yeah.
Otherwise, we can change in variable exposure. We can change the values.
Yes, you can. You can change. So you normally like we use a variable, and the values we just specify at the beginning.
Okay.
Then you don't need to change your code.
We don't change the code.
Yeah, you don't change. You only change the values. Yeah, in the given condition part. Yeah. Because if you change the value, then you have to everywhere you have to change.
Everywhere we have to change.
Yeah. Mm-hmm. So that's what we are having over here. Then this part is the initial condition. Remember in the slides, I said the XS, the first position, is a 0. So here I set up that initially is a 0. Then this part, the for loop part, that's the most important part. Yeah, that will be calculated. First we said we calculate x2, x3, x4. But here with this loop, then it will automatically calculate for you. If you have 100 years, it will do 100 times. Yeah, if 20 years, they do 20 times. Yeah.
We can give the how many years required. How we can.
So over here, it determined by those sediment data file. If that data file we have 20 years, we do 20 years. But you can also make change. So where you make is here.
Range.
Yeah. So length of year, for example, here we have 20 years, then it will do 20 minus 1. Yeah. But if you have 100, you can put 100 minus 1. Length of YR, which means like, if in Python, length function gives you how many elements for that vector, for that array. So this is a programming part. So for this is a loop. It starts from I equal to 1, and then next one will be taking I equal to 2, Y equal to 3, and so on.
you have any QY, QX calculation file, QX, capital QX.
That's
You
a
are given the data sediment data, year under sediment data 142 and
so that's
sediment
from
data,
here, QX.
You are given the sediment data in the separate file, sediment year and sediment volume.
Yeah.
You are given.
That's in the file. Did you copy the file? Did
I
you?
copy the file, madam. How we can calculate it in the?
It will be, there is a function, there is a load function. This function load. So all this data file has been loaded to QX.
We didn't have QX data.
QX is in this sediment.txt file.
We didn't have QX data. How we can calculate it?
If you don't have,
We don't have.
okay, then the information is missing. You don't have like a sufficient information for using to solve this problem over here. So that will depend on, remember in that last slide, I rearranged the equation. Only the unknown is on the left-hand side. Everything on the right-hand side is known, is given.
Okay.
So if QX, if you don't have that, then you can have,
We can calculate the QX value.
if you have, other information from other source. It's not, you have to do the calculation, you do the calculation.
That value also, that calculation also included in this math, in this program.
That's you have to use what equation you are using. You just replace this part.
Okay.
You
Sediment
just,
data.
you just replace this part. Use the formula you are using.
Okay.
Like you calculate, later we calculate this QYS and QYN. You calculate QX as well. Good. So then you will do all those calculations, and then that's the formula you are using. After the loop is done, basically you have all your XS in. But here, I also load this shoreline data. That is the aerial information I mentioned before. You are going to use that to compare with your model result. Then you plot the result. Very simple. Actually, it's very simple. This model is really simple. Like those, this is all plotting. That just help you to see the result. The key part is here, the for loop. That's a finite difference method. So that's the key part. Now you are able to run the whole model.
Control all.
So that's a result I'm having. The blue lines are simulated. That's from that loop. This red dot, that's from that measurement. So you can see initially they have a better agreement, but later actually the discrepancy is bigger. So you have to think about, for this model, for this data set I'm using here, for the 20 years I use all the same wave data. So that's accuracy you have to think about. And also for this data set over here, you just, if you have more accurate one, you change it. That's one thing. And another thing is for the k-value, like you mentioned before, you are able to use more, like yearly variation or monthly variation. So those data sets you are using. And also here, this we are doing is yearly. But we know, like different season, the wave condition is very much different. So if you want to have more accurate one, you can use a shorter, like a monthly, to do it, rather than yearly. So then your delta T can be smaller.
Smaller.
Yeah. So that's another things you are able to do. So simple model, but it can help you to do some estimations. So you're able to run it? No problem. And also for the MATLAB. Sorry?
I'm not able to run it actually.
You can't run it?
Yes.
Do you have what's the error message?
Error message now, some variable is not defined.
In console it is doing
It's in Python?
Yeah, this is in Python.
Is your data file everything in the same folder, same path?
Yeah, same folder.
And did you change your folder to this one?
Folder, no, like we had a separate folder in desktop. From that we
You copy everything in one folder?
one folder.
And did you change your directory to this one? Did you change this one? Your working folder. Change your working folder to where you saved your file.
I can't find it.
So
It's
You-
not coming like that.
okay, can you just go to the view,
Yeah.
then go to the Windows layout, go to the MATLAB, MATLAB layout.
Okay.
Yeah. And then you change your folder to that folder. You have your file.
Question two. Question two only, yeah.
So you are here.
Yes.
Everything is here.
Yes.
Okay. Then you run everything.
Same thing. Console is only.
Can I just have a look? I
Yeah,
just
yeah,
couldn't
sure.
see clearly.
Sure, sure. It is like quite very small.
Oh, it's running.
It's running.
That's no problem. Yeah. You just click plot.
Plot quickly.
Yeah.
Yes.
Yeah. So you have to open that plot window. But it's too small, then you undock it. Undock.
Okay.
Yeah, then you
With this we
can.
can view it. Okay.
Yeah, then you can
Okay.
see better.
Thank you.
Yeah, no problem. Yeah, so you're installing. Yeah, actually, I feel this Spider is really good to use, especially if you are familiar with MATLAB. Very easy to work on different one. Okay, so yeah, you have the code you can play with, and also you can do modification. You can improve it, and even you can, if you have better result or better model, we can exchange. Yeah. So, do you have any more questions? I know today is your special day, so yeah, we won't delay the lecture finish time. So we'll see you tomorrow. Thank you.